Talk about the Sirius library, an open source generic circuit folding framework, and with application to the zkEVM circuit. This is a joint work with my colleague Mikhail. My talk consists of three parts. The first part, I will give a brief introduction for the overall architecture of the library. The second part, I will dive deep into how do we fold in the zkEVM circuit. And the last part, I'll talk about the cyclefold, which is a feature we're currently implementing. So the first part, the introduction part, the problem we are going to solve is trying to, suppose we have a function, I've given an initial state, Z0. We apply the same function multiple times, we get a final state, Zn, and we try to prove the n steps of computation is correctly. So this is fit into the IVC domain, which stands for the incremental verifiable computation. So at each step, for example, at step I, we will have an input Zi, and we apply some function f with some private witness data Wi. We will get the output Zi plus 1. So this is just one step of computation. And the whole purpose is the prover will fold it to the all n steps of computation, and the verifier will verify it at the end just by once. So after it verifies n step of computation, then the verifier just verifies the final proof. And if the verifier of the final proof is correct, it means all the n steps of computation is correct. So there are various applications. For example, the verifiable delay function zkRof and zkEVM. So today we will focus about the application for the zkEVM. In the zkEVM, you can think about the f is the instruction, and the state is the value on the register, and on the memory, we can get a fingerprint of all the value. So each time you apply an instruction, it actually either modifies the register value or the memory value. So you can view this as a state machine. So this fit into this IVC domain as well. And so because we have plenty of time today, if you have any questions, feel free to interrupt. The architecture of Sirius actually consists of three layers: the front layer, the middle layer, and the backend layer. The front layer we also called arithmetic layer. So starting from the front layer, you actually, so this is because we are folding the Halo 2 circuit, so the user will have a Halo 2 circuit to be folded. And the Halo 2 circuit usually consists of two parts. It will define the custom gate as well as a bunch of lookup arguments. So the front layer is responsible to convert the custom gate and the lookup arguments into some intermediate representation, which can be folded by the middle layer. So after the conversion of the arithmetic layer or the first front layer, we will enter the middle layer, which is the core part of the library. We call it the folding scheme layer. So in the folding scheme layer, what we have before is we call the Sangaria IVC folding. And currently we are migrating to or implementing the new feature to change it to the cyclefold folding scheme, which I will explain in the third part. So inside the cyclefold, there are actually two major components. One is the protogalaxy verifier, one is the Sangaria verifier. They actually both be used as part of the IVC folding circuit. At the end, which is the backend layer, we can also call it the decider layer, which means after you fold it n steps, at the end, the verifier or the prover will create a succinct proof to be verified by the verifier. So after the verifier verifies the proof by the Snark layer, it actually can make sure the whole n steps of computation is executed correctly. So that is a very high-level architecture of this library. So the second part, I'll talk about how do we fold in the zkEVM circuit. But before that, let me briefly introduce what, as a developer point of view, what kind of modification you have to do with your circuit so it can be applied by our library. So if you have familiar with the Halo 2 circuit, it actually, all the developer, if you develop any Halo 2 circuit, you have to implement the circuit trait, the Halo 2, circuit trait. So inside this trait, there are actually two functions you have to implement. The first is the config function. The second one is the synthesize. So for the configure function is where you define the layout of your circuit. So when I mean layout, it means it has a bunch of fixed column, a bunch of advanced column, and you have to define the relation of the circuit. It can be multiple custom gate circuit. You can define your lookup. So with all the setup, it actually set up the circuit structure. So this is the config function. You can also assuming this is the setup phase. And the synthesize function is kind of like a runtime. So given a specific private input and the public input, you fill the data into the table. So in the Halo 2 circuit, you can imagine this is a big table. It has a bunch of columns. So when you set up, you actually define the layout of the table, like how many columns, what type of columns, and what kind of gate. So in the synthesize step, you actually fill the data into these columns. So you will fill the fixed data, which is fixed data means it's fixed. You cannot change it. And the advanced data or advanced column is actually you can change it every time. For example, if you're doing some Poseidon hash, the fixed data will be some, for example, the constant of the Poseidon hash, like x to the power of 5. The 5 is kind of constant. It belongs to the fixed data. And when you hash different stuff, you actually calling this same circuit but with different private data. So the synthesize step is actually how do you fill the private data into the circuit. So when we do the so when you try to modify the Halo 2 circuit into our to be usable by our folding library, you actually also have to implement these two functions, the configure and the synthesize, but we call it the synthesize step. But for the first function, the configure function, you actually don't have to do anything. You just, if you already have a circuit, you're just using the same function configure here, because the layout, we will not change it. And the second step, or the synthesize function, you actually will modify it a little bit and change the name as synthesize step. So what the difference is, in the synthesize function, you actually will have two input, the configure and the layouter. But in our synthesize step function, you actually will fill in the z in and z out, which is the state in and state out. Because as IVC, you have to define your state input and state output, and the function f will be that circuit. So this is what you need to do as a developer if you're trying to adapt your Halo 2 circuit to be the folding circuit can be folded by the Sirius library. And the arity here is actually just the length of the vector. So depending on what is the state defined in your application, it can be one single value or some length n vector. So now this is how we do for whatever circuit, including the zkEVM circuit. So next, this is the architecture of the zkEVM circuit. I just grabbed it online. It's very complicated, as you can see. And the lucky thing is, if we want to turn out this big giant circuit into the step folding circuit, we don't have to modify most part of it, only to touch a little bit part of it. So actually, for me, I also don't understand fully of all the components and how they interplay, but I just try to find where is the state in and state out. So if you're familiar with the EVM virtual machine, the EVM has a world state. So it has a state tree, and everything of the state tree is actually Merkleized. So if you can get the Merkle root of the state tree, you actually get everything of the state. So as an EVM circuit, or as an EVM virtual machine, the state function is just the state root or the state tree. And the function of each step is actually a bunch of transactions, or maybe just one transactions. So given one transactions, it will modify some of the state. So this is the EVM machine, how it works. So with that in mind, my goal is to find where is the state root. So this is actually here, the public input circuit. Here it defines the previous state root and current state root. And when you apply any transactions, it will modify the state root. So this is a part of the circuit we are going to modify. And of course, each of these components, you can imagine the sub-circuit in a giant circuit. So in Halo 2, as I mentioned, the circuit is a big table. So each of these sub-circuit is actually part of the table. So just consists of multiple polens. So let's say in total we have 1,000 columns. So each of these components maybe consists of 100 columns or 15 columns. So that is how do you visualize these guys. And of course, between these tables, there will be some relation or interactions. So that means this is defined by the copy constraint or lookup. So the copy constraint is a special term in the Halo 2, and the lookup is kind of widely used in Halo 2 or other like a zk proof system. But we are not going into detail of this. So how do we modify the circuit? It actually, we only need to do like 300 to 400 lines of modification, including the circuit part modification and the prover part of modification. We are able to modify the zkEVM circuit into some Sirius foldable circuit, and we can apply our prover to fold it. So it's actually quite neat. So as I mentioned, we will define the Z-in and Z-out as previous state root and current state root. And the function f, you can imagine just one transaction or a bunch of transactions. It will modify the state root. And the W is all the necessary auxiliary data, including the transactions or some other like metadata. And we will, after we define the in and the out, we will just modify the public input circuit a little bit and expose the in and the out to the upper level. Because from the architecture point of view, everything is under the silver circuit, the giant circuit, just in this graph. So after we modify the pi circuit, we will expose the in and the out into the silver circuit. So a little bit of modification for the silver circuit. With that, we are able to modify, or we are able to fold it, the zkEVM circuit. And if you want to know the detail, there is a more detailed version of the documentation. How do we do the modifications? But here I will just skip it. And of course, during the modification, which part is easy, we also encounter some challenges. So I will just list 3 major challenges. So the first one is the folding of public input. So in the zkEVM circuit, he has a public input, which is the hash of previous state root, current state root, transaction root, and Coinbase, so a bunch of important data to make sure the data is really from the blockchain. And you might think we can just do like the folding. We do some random linear combination of the public input column. And each step, we create a random number and fold it into the accumulator column. But actually, this will not work. This is because during each step, the random number R is actually created from the fat shamir, which absorbs the commitment of the data, and then create a random number for each step. However, from the verifier point of view, during each step, the verifier actually is not play with the prover. He just wait until the prover done all the stuff. So he don't know what is the randomness number R for each step. So it means if you don't know the R, you cannot get the folded value using the random linear combination with the public input, and you cannot verify the public input. So that is the first difficulty we have to encounter. The second one is, I think in the OEM slides also mentioned, the zkEVM circuit is a very large circuit. It has about 2,000 gates. So in our previous version, the Sangera type IBC, we actually symbolically combine all these gates. So if you have a 2,000 gate, you actually have a 2,000 degree, if you combine together, 2,000 degree polynomial. That is blew up if you want to calculate the constant in the Sangera. This is something we cannot proceed with the Sangera type IBC. And the third challenge is a large number of columns. As you can see, we have about 1,000 columns. And in the folding, because when we commit the witness data, we actually try to concatenate all the columns into a big long vector and commit that long vector. The reason is when you do the commitment, we are using the ECC type commitment. So it means each commitment is a point on the elliptic curve. And when you do the folding of the commitment, it's actually the multiplication or the addition of the elliptic curve point. So that is very expensive when you write it in the circuit. We try to minimize the number of commitment. So that's the reason we are trying to concatenate all the columns into one single vector. However, with this kind of number of column. If you concatenate 1,000 column together, you actually have you just 1,000 double the commitment key size. So let's say if you have 1 gigabyte commitment key in the zkEVM circuit, then in the folding we have 1 TB commitment key. That is very large to fit into the memory and also load from the disk. It's not efficient. So this is 3 major challenges we have after we folded the zkEVM circuit. So the solution is, so for the first one, actually, since we cannot using the normal random linear combination of the public input columns, so what we can do is actually, we feed this public input value or each step as a device column, a device value into the IVC part of the circuit, and we copy constraint it to the public column. So before, when you define the zkEVM circuit or alien user-defined circuit, you actually, how do you make sure it's public verifiable? You actually is made a copy constraint, which means an equivalence relation, they must be equal. So some private data from the user-defined circuit must be equal the public input circuit. So this is what we call the copy constraint. This is the equivalence relation. So now we feed this data as into our folding part circuit. We define the equivalence relation, which is copy constraint. So you actually establish an equivalence relation between the IVC part circuit into the user-defined circuit. So after you establish this equivalence relation, you can just throw away the public column, because in either way we cannot verify it, but we already have the equivalence relation between the user-defined circuit data to our IVC folding circuit data. So after that, we are able to using some simple accumulation scheme to easy to calculate for the verifier. So that will be very easy. So let's say at each step you have a new public value. You just hash it into the existing one. So each time you hash it into the existing accumulator value. So hash of the something, you hash it again. So with this, the verifier is easy to verify because the verifier knows the public input value of each step. So he can just hash them one by one. And there is no hidden random number he don't know. So the verifier can easily hash it at the step n, and he can get the accumulated public value from all the steps. So this is how we overcome the first challenge. So for the second challenge, where we have a large number of gates, the solution is we just using the protogalaxy protocol to replace the Sangria protocol. Since this is not our topic today, itself is a complicated topic, we will just skip it, the protogalaxy. But the idea is the protogalaxy can deal with large number of gates. So this problem is also solved. Then third challenge is the large number of columns. So with a large number of columns, this is actually the design trade-off between the number of witness commitments, so number of commitments, which means the number of ECC operations in the circuit, versus the commitment key size. So this will change our circuit a little bit, not just concatenate all the column data into a big giant vector and commit it. We actually can split it into several parts. So we can adjust the parameter to do some trade-off between the folding circuit size and the commitment key size to make it balanced. So this is how we're going to solve the third one. And the first two is already done. And the third one, we are going to implement it after we finish the cyclefold part. So the next slides, I will describe a little bit the difference between the Sirius prover and the zkEVM prover. So when I mean the zkEVM prover, I specifically mean the screws version. So actually in the Ouyang's talk in the last talk, he also mentioned there are 4-layer structure. So it means the layer 0 is you have a circuit, super circuit, it actually proves one or multiple blocks. Depending on the large of how many transactions in the block, if you can fit the block into the fixed size circuit. So sometimes if the block is large, you probably can only fit one block of transaction into the circuit. If the block is small, you might be fit multiple blocks into the one circuit. And let's say if you fill two blocks into the circuit, you're still missing something not filled, we just pad it by some dummy data. So this is how it works. So after you have the first layer, you have a bunch of blocks. The screws prover will just create a proof for each circuit or each block. So this is layer 0 proof. After that, if you move to the next layer in the prover tree, it actually either compress the proof or accumulate the proof. When I mean the compressed proof, I mean, for example, I just mentioned original circuit is 1,000 columns, right? So here we are using some recursive circuit to compress it into less than 100 columns. So the proof size, everything is smaller. So this is the compressed layer. And the compression layer or the aggregation layer is just prove multiple proofs together. So let's say if you have 5 or 10 proofs, we prove together. So this is how to reduce a bunch of block proofs into a single one at the end. So this is the layered structure of the Scrolls zkEVM prover. And for our folding scheme, we don't have tree structure. We have like a linked list structure, like a line. So it's easier. What it does is for each steel giant circuit, we will create partially proof, like you fill the data with witness data, make the commitment, and do some protocol level needed calculation, and you fold it into the accumulator. So it means each time we don't have to create a fully proof, just kind of create a partially proof and fold it into the accumulator. At the end, we have just one accumulator instance. We can verify it. So as you can see, each time we actually do less work at each step. So in principle, it will be faster than the 4-layer structure. Also, the architecture level is also easier. So that is the overall difference between the folding scheme prover and the current existing zkEVM prover using a recursive snark. So this is a briefly overview of how do we modify the circuit from the zkEVM to be foldable by our folding scheme, and as well as the prover structure. So next, I will talk about the cyclefold. This is a folding scheme we are trying to implement right now. It also will be helpful to make the zkEVM circuit folding faster. Yeah. So that is, and first I will introduce what we have now, which is the cycles of ellipse curves. This is a Sangera type folding, or previously, how do we do the folding? So as I mentioned, because our commitment is on the ECC curve. So a commitment is actually a point on the ellipse curve point. And if you're familiar with the ECC curve, it has two fields. One is the scalar fields, one is the base field. These two fields is different. And when we build a constraint system or circuit, it naturally lies into the scalar field. So everything happens, all the commitment, all the number actually, like x plus y equals z or x times y equals z, this number is actually happen in the scalar field. However, the commitment is a point on the curve. It consists of x, y point. So x, y point is actually x and y is in the base field. It's a different field. So if you want to do the ECC operation for the commitment, like when you fold the 2 point, you actually is a plus lambda times b. A b is just on base field number. So this is happens in the base field. So one naive way is emulate all the base field operation using the scalar field. That is very heavy and makes the circuit very large. That's the reason people designed the cycles of ellipse curves. So what does it mean is, for example, the BN256 curve, it has two fields. So we find the dual curve, which is called the grouping curve. So the scalar field of BN256 is equal to the base field of the grouping curve. And the base field of the BN256 curve equals the scalar field of grouping curve. So it means whenever you want to operate on the base field of BN256, you can also operate on the scalar field of the grouping curve. So that's the reason we have this part is a circuit defined on the BN256 curve. And this is a circuit defined on the grouping curve. And whenever you want to fold this, the instance generated from this circuit, the commitment, for example, it actually is base field of this native field. We have to move it to here. So the folding computation is actually done in this part. However, if you're trying to fold the instance from the upper part in here, you actually also to make sure the calculation of this circuit is correct. So it means this circuit will itself generate some witness, some trace, and some instance. When I mean instance, it's just commitment or its columns. So you have to fold this guy as well. And this can be done by here. So it's kind of intertwined, right? At each step, you actually do something in this primary circuit, you do something in the secondary circuit. This is one step. In the next step, it will grab the input from output from here to fold it again, and vice versa. So this makes the whole architecture a little bit complex. Also, our main purpose is to make sure this calculation is correct. But here, in the secondary circuit, we don't have any need to the step circuit calculation. So it's a dummy. But we have to duplicate everything. So the fold part, the circuit is actually duplicated, and it's kind of unnecessary. So this is something we try to minimize the redundancy work. That's the reason we introduced the cyclefold. So the cyclefold idea is kind of similar to the cycles of elliptic curves, but we're trying to move everything in one circuit. So we try to do all the folding or all the calculation in one circuit. However, so in this case, let me introduce a terminology. So this is the primary circuit, and here we call it the step folding circuit. And the second circuit, we just throw it away, the secondary circuit. But we will define a support circuit which only do the ECC operation, so a minor circuit. This circuit, the instance, we call it the UI star. So it means this circuit will fold both itself and another smaller circuit. So he will do three things. The first thing is make sure the execution of one step of calculation F is correct. The second step is folding of this circuit itself. The third part is folding of the support circuit. I just explain what is that. So when you do the folding of this guy, the capital UI and little UI, it consists of the elliptic curve point. You do some operation on that. This is a non-native operation. So we have to delegate it out or outsourcing it out. We're outsourcing this calculation to the support circuit, which only consists of a ECC operation. So let's say, as a proof point of view, I get this data from previous step, and I try to do the delegation computation. I just feed these guys into some smaller circuit. We get the correct computation answer here. So this will give the correct computation input and output here. And we still have to fold the support circuit, because how do we know the support circuit is done correctly? We have to fold its traces to make sure at the end everything is correct. So to fold this one, we have to know what is the UI star. So actually, it means when you're trying to create this circuit, you first create the input of the circuit. It can be done in two steps. So the first is we get this data from previous step of the circuit. And then from here, we feed this into some support circuit, and we will get the trace of that circuit, the commitment of trace of that circuit, and we can feed it into this circuit. So it means when you prepare the generation of this circuit, we actually prepare it by two steps. First, get the capital UI, little UI from previous step. Second, do some offline stuff to feed into the support circuit or smaller circuit, only do the ECC operation circuit to get its trace. So now we get everything of the trace, and we can synthesize or fill the data into this circuit to get this trace. After you get this trace and commitment, you can move to the next step. As you can see, from the architecture point of view, it's much easier because we don't have the intervening stuff, right? Like here, you have to do synthesis of this circuit and do the synthesis of this circuit and move on. Now we just do two steps offline and just have one single circuit. So also we remove some redundancy part, because when you're folding the UP, the primary circuit instance, this part, the circuit is big. If you move everything into here, you actually have smaller redundancy. So in general, this will improve this overall circuit computation, probably 40% or 30 to 40% at least. So that is the architecture of cyclefold. It's a little bit complicated if you first know it. Yeah, it's hard to explain actually. But I will try to give you just a general idea. Yeah. And this is the more complete structure of how it goes. It adds more details. So, but definitely we are going to explain that detail here. I just give you some impression. This is still a complicated circuit design. Yeah, so that's all my talk.